All right, let's talk about one of the coolest, most elegant tricks in all of engineering, cam design. We're going to dive into how a simple spinning shape, it could be a weird oval or even something that looks like a heart, can create these incredibly complex and super precise movements in machines all around us.
So that really brings up a fascinating question, right? How in the world can you get a machine to do something really specific, something that's not just a simple circle, using nothing more than a constant spinning motor? Well, the answer is, it's just brilliant.
And it's all thanks to this clever little device, the cam. You can almost think of it like a mechanical programmer. Its very shape is the code. It's a physical program that tells another part exactly what to do, how to move, and precisely when to do it.
Okay, so to really get how this mechanical brain works, we've got to meet the two main characters in this story. The cam, of course, and then the part that actually reads its instructions.
So, first up, you have the cam. This is the boss. It's the driver of the whole operation. Its unique shape, that carefully designed contour, that's basically the source code for the entire movement. As this thing spins, its profile is dictating everything that happens next.
And then you have this guy, the follower. This is the component that actually reads that code. It just traces along the cam's surface, and its motion, whether it's moving up and down or back and forth or maybe swinging in an arc, is a direct result of whatever shape the cam has. So that's the fundamental partnership, right? The cam does something super simple. It just spins, but the follower is forced to do something way more complex. It's an absolutely brilliant example of mechanical transformation.
And trust me, once you know what to look for, you see these things everywhere. They're ticking away inside old clocks, they're guiding the super precise movements of robots on an assembly line, they're even used to position things on satellites. Cams are pretty much the unsung heroes of any kind of automated motion.
Okay, but for this whole system to work, there's one absolutely critical rule. The follower has to stay glued to the cam's surface at all times. If it separates, the program is useless. So how do engineers make sure that happens?
Well, there are basically two main ways to do it. On one hand, you can use an outside force, like a spring, that's just constantly pushing the follower against the cam. Or you can just physically trap the follower inside a groove or a track so it has no choice but to follow along.
And of course, each approach has its own pros and cons. The force-closed systems with a spring are usually simpler and cheaper. But if you go too fast, the follower can literally jump right off the cam. It's a phenomenon called follower float. The form-closed systems with a track, on the other hand, give you positive control, no jumping possible. But they can introduce more friction and wear inside that track.
All right, let's talk about the sheer variety of these things. This is definitely not a one-size-fits-all situation. It's more like a whole zoo of different cams and followers, each one shaped for a very specific job. So here's the classic, the plate cam or disc cam. This is probably what pops into your head when you hear the word cam. The follower just rides along that outer edge, and as the radius of the cam gets bigger or smaller, the follower gets pushed out or it's allowed to come back in. Simple as that. But then you've got something totally different, like a barrel cam. See how the follower rides in a groove that's cut into a cylinder? This creates motion that's actually parallel to the axis it's spinning on. These are super useful for things like rotary indexers, where you need to turn and move something at the same time. And it's not just the cams. The followers are just as diverse. Check out the roller follower on the left. That little wheel on the end is basically a tiny bearing, and it's all about reducing friction so you can run things really fast and smooth. Then on the right, you have a flat face follower. Much simpler, but that wide surface means it can handle a lot more force and deal with some really aggressive cam shapes.
Okay, so we've got the parts, we've got the shapes. Seems pretty straightforward, right? Well, this is where things get really interesting, because there is a massive, hidden problem lurking just beneath the surface, and it's the key to what makes cam design so brilliant.
So, any cam's motion program can be broken down into a few simple phases. You've got the rise, which is when the follower is moving out. Then there's the dwell, where it just sits still for a bit. And finally, the fall, where it comes back. The real challenge, the whole secret, is how you design the transitions between these phases.
Now check this out. Let's say you try the most simple, intuitive design you can think of. Just make the follower move at a constant speed during the rise and fall. Makes sense, right? Wrong. Look at that middle graph. The velocity just instantly jumps from 0 to a fixed number. And to make that happen, look at the bottom graph. The acceleration has to spike to infinity. In the real world, infinite acceleration means an infinite force, and infinite force means your machine just blew itself to pieces. Total, catastrophic failure. And this introduces us to the true villain of mechanical design, a thing called jerk. Jerk is literally the rate of change of acceleration. It's that sudden jolt you feel. And in a machine, high jerk means violent shaking, a ton of noise, and parts that will literally vibrate until they break. And yeah, infinite acceleration, that means infinite jerk, the ultimate enemy.
So how on earth do you design around this? How do you avoid this machine destroying infinite force? Well, it turns out you just have to follow one simple but incredibly powerful rule. The solution is so elegant. It's called Norton's fundamental law of cam design, and it basically says this: the functions that describe your follower's motion must be smooth and continuous for both velocity and acceleration. No sharp corners, no sudden jumps. If you can make those curves smooth, then the jerk, that bottom graph, will always be a finite, manageable number. You've tamed the beast. And just look at the difference this makes. On the left, you've got a design called simple harmonic motion. See how that acceleration graph just starts and stops abruptly? Those sharp corners create those nasty infinite jerk spikes at the bottom. That's bad. Now look at the design on the right, a modified trapezoidal curve. The acceleration curve is beautifully smooth and continuous. And what does that give you? A jerk profile that is finite and perfectly well-behaved. That is the secret to good cam design.
So, the big takeaway here is that designing a good cam isn't just about making sure the follower gets from point A to point B, it's all about making sure that the entire journey, what engineers call the SVA-J curves for position, velocity, acceleration, and jerk, is perfectly smooth and continuous from start to finish.
And why do we care so much about this? Because when you follow that one fundamental law, your machines can run faster, they're way quieter, and they last so much longer without shaking themselves apart. It is literally the secret sauce behind high-speed, reliable automation.